Hey guys, welcome back to day 12, Equilibrium. Today we're going to dive into the fact that reactions aren't always one direction. That reactions sometimes can go and proceed, so to speak, in both ways. Prime example would be breathing. Oxygen, we breathe in air, the oxygen comes in, ultimately goes to the hemoglobin, onto the iron metal center in the hemoglobin, is transported to where the blood takes it, and the oxygen comes off the hemoglobin. So it's very important for oxygen to go onto the hemoglobin and then come off the hemoglobin to go into the cells to do what it needs to do. That means that the reaction is not a one directional thing. At this point, up to this point, most of our reactions were one direction. I mean, think about what we do in our everyday lives. You cook, you cook something, whether it's eggs or whatever you're cooking on this, however you're cooking it, it's a one directional thing. Eating's one directional. Gasoline or fuel, one directional. What One thing that we use all the time now, cell phones, we can reverse that reaction by putting electrons back into the battery, and so we can use the cell phone again the next day without it being plugged in. So when we have a reaction, we know that there's reactants react and products are produced. And typically we're speaking, we've always had the reaction go in the forward direction. And that has a rate constant, K, in the forward direction. However, we have now this double-headed arrow. A lot of times, just note, you'll see the arrow as this arrow like this. You'll see arrows like that, where they're half arrows. You have to do it half arrows. If you draw two full arrows, that's fine. Sometimes you'll even see it as an arrow, one arrow with two heads. Either way works for me. We have a K forward direction. Now we have a K backwards reaction, or K reverse. So I'm going to KB, or sometimes you'll see it as KR. Either way, it's the backward reaction. So what happens? Both of these reactions have a rate. The rate constant or rate law for the reaction in the forward direction, reactants going to products, would be K forward times the concentration of the reactants. There we go. All right. However, because the reaction can proceed in both the directions, some will say reaction can proceed in both directions, we are also going to have a rate equals KB or KR times the products. So I have a rate law for the forward reaction, and I have a rate law for the backwards reaction. Now, this term equilibrium. Long word, write it a lot. Equilibrium is reached when the rate forward equals the rate reverse. Or backwards. Does that make sense, hopefully? If it doesn't, well, let's dive in more. So what I'm going to say here is that the concentrations of reactants and products no longer change with time. So this is a dynamic situation. Like sometimes they even say dynamic equilibrium. So when I say dynamic, it means it's in constant motion, unlike static, where a good example of a static equilibrium or a static situation, not static equilibrium. A static situation was like when I went to a junior high dance, where you walk in with a date and the boys and girls separate to the different sides of the dance. That was a very static situation. Here in equilibrium, it's kind of like a bridge or a busy airport terminal where there's people coming and going at all times. So at a major airport, there's probably during the day between about 6 a.m. and probably 8 p.m. There's about a constant amount of people in that airport, most likely. It's a major one. However, there are people constantly coming and going. But the overall concentration of people in that airport is pretty much the same throughout the day. So it's a very dynamic situation because you have flights leaving, flights arriving, you have people coming to the airport, people going away from the airport. But overall, the number of people in that airport is pretty constant throughout the day. I would imagine. I'm sure I'm not in that industry, so I don't know. But that's just you can probably visualize an airport and visualize that the people are coming and going, but there's still a lot of people in the airport, and it's not really changing much throughout the day. For a reaction, once the reaction proceeds and equilibrium is reached, it means the rate forward of the reaction, however fast we're going, is equal to the rate reversed. And it's not a static situation, it's a very dynamic situation. But if we unpack this, the rate forward equals the rate reversed. So the rate forward equals the rate reverse in this dynamic situation. Well, the rate forward is also equal to the rate constant forward times the concentration of reactants. And the rate reverse, or the rate backwards, is KB times the concentration of products. And they are equal to each other. So what we're going to do is we're going to get the K's on one side and the concentration on the other. So I have KF divided by KB equals the concentration of products over the concentration of reactants. And what we do is we define a new variable called capital K for equilibrium. This is our equilibrium constant. So K is equal to the concentration of products over reactants. So capital K is equal to the concentration of products over the reactants. And it tells us, this is very important, K tells us how far a reaction proceeds. So the concentration of products over reactants. So if the products is a big number and reactants is a small number, K is very, very big. If the products is a really, really small number and the reactants is a big number, K is very, very small. So the bigger K is, the more the reaction goes towards completion. And so if I have a generic reaction, A, B, C, D, and they have coefficients. Let's say they have coefficients X, Y, I don't know, alpha and beta. There we go. So K then, equilibrium constant, and it's capital K, is equal to the concentration of products, concentration of C, concentration of D, overreactants, concentration of A, concentration of B. However, we raise them to their coefficients. So C is to the alpha, D is to the beta, A to the X, B to the Y. And so that's what happens. Now, this is not the complete story. It actually has to do with the law of mass action and activity, but we don't learn that for many years. So this will be a very good approximation for K. Very good. Now, if we go back way up here, we know that K here, K is the rate constant determined from experiment, and it is temperature dependent. Since K is temperature dependent, these are both temperature dependent, which means this guy, K, is temperature dependent. So all the K's in the book are at 25 degrees Celsius, unless otherwise told you. And sometimes they do tell you for the problem. So K, again, tells us how far the reaction proceeds. So K can be three options. We're going to call it K is going to be, and it's all compared to 1, 1, 1, and 1. So, of course, K can be much, much less than 1, which we're going to call small. And that's usually 10 to the negative third or smaller, right? And we are reactant favored. Not many go. K can equal 1, and that means we have a significant amount of products and reactants. And lastly, K can be bigger than 1, and a lot of times we call this large, and it's about 10 to the third, and it is product favored. And so obviously, when I say K equals 1, anything from about 0.001 to about 1,000, we pretty much say that's K is in the close to the 1 range. At least that's how we're going to look at it, because we're going to have a significant amount of products and reactants in the solution. You know, and a good way to think about this, how big is K? And I relate it to pennies. If K is really, really small, I can give you that many pennies for the rest of your life every day, and I would never give you a penny. Right? 10 to the negative 10th, 10 to the negative 15th, 10 to the negative 27th. Those exist. Tiny. However, really, really big, 10 to the ninth. How far would you go to get to 10 to the ninth pennies? I mean, honestly, you could actually carry that many pennies, but let's just say that much money. 10 to the ninth pennies would be 10 to the seventh dollars. Right? That's $10 million. Most of us will go anywhere in the country, maybe even anywhere in the world, to get $10 million in our bank account. Right? That's a lot of money for most of us that take this class. Some of us, 10 million. To Bill Gates, $10 million is a good sum of money, but it's not. It's not the same as it would be for me. I would pretty much go anywhere to get $10 million if I could do it, and I had a pretty good chance of coming back. And so that's how I can tell is a lot. 1,000 pennies. Well, how far would you go for 1,000 pennies? I wouldn't go very far. 1 penny wouldn't go very far. 10 to the 12 pennies, I'd go pretty far for 10 to the 12 pennies. So that's how I tell you if K is big or not. Like, how do I tell if it's big? That's how I tell if it's big. It may work for you, may not, but that's how I tell. So now let's look at a little example here, an actual example. Because one thing that I had a problem with as a student was I used to think of always a before and after for a reaction. Right? Kind of like those weight loss ads you see in the magazine where there's this person that's not in shape with the head, and then the same head on a person that's in shape. We know Photoshop exists, but if you just take this pill and be thin, everybody would do it. Obviously, it's not true. So when we talk about reactions, though, I had the same picture of that ad in my mind. Like, oh, there's a before and there's an after. There's the wood before we burn it, and then there's the fire pit after we burn the wood, before and after. That's no longer the case. So hydrofluoric acid is a weak acid because it's not one of our 7 strong acids. So hydrofluoric acid plus water, because it's in water, is in equilibrium with hydronium and fluoride. So if I initially start with 0.10 molar, what happens? Well, and it's a weak acid. What's going to happen? Well, I'm going to have stuff in my container. So if I make this container, let's say it's just a beaker, which probably wouldn't be, let's say, a plastic beaker. HF reacts with glass. And there's my liquid. So in here, I will have HF. And I will have, of course, water. I don't want purple for water. I want blue for water. A lot of water. Lots of water. I'll have hydronium. And I'll have fluoride. I have concentrations of all of these. They're all in there. A lot of water, but they're all in there. So now my equilibrium constant K here, capital K. Now we'll eventually get to that this is going to be a Ka. We don't know that yet in the book. It's Ka for it because hydrofluoric acid is a weak acid. Which, little side note, how do I know it's a weak acid? Well, it's not one of our 7 strong acids. So 7 strong acids HCl, HBr, HI. Right, 3 middle halogens. Then we have H2SO4 sulfuric, nitric, perchloric, HCl4, and then HClO3 chloric. Those are our 7 strong acids. Okay, go back to this example. Products, hydronium, H3O+, fluoride, F-, all over HF. Note, right, water is omitted. Put H3O down. How about H2O? Water is omitted. Right? The concentration of solids and pure liquids are omitted from the equilibrium constant expression. Right? Why are they omitted from the equilibrium constant expression? And the reason is solids, think about a solid. If I double the amount of solid, does it change the concentration? No. And the reason is solids do not expand to fill their container. Neither do liquids. And they're not going to, like the water is, it fills its container, but it's not going, like if I add water, it's already there. So solids and liquids do not expand to fill their container. Gases do. And when things dissolve, they will, spread out to fill the container. And their concentration, their particle per volume ratio changes. But if I add more solid, or if I add more water, what happens if I add more water to this example with HF, all I'm going to do is lower the concentration of these 3. I'm not really changing the concentration of water much. So we just ignore solids and liquids from the equilibrium constant expression. Okay, so now we have this equilibrium constant K. However, there are hundreds of millions of reactions out there. New ones are being tried to be found all the time, every day. And so sometimes we're going to have to manipulate the reaction constant, or the equilibrium constant. So we're going to manipulation of K. There are three ways we can manipulate K. The first one, if I reverse the reaction. If we reverse the reaction, we invert K. Well, remember Ka right here, or K was hydronium fluoride HF. If I reverse the reaction, so now we have H3O plus aqueous plus F minus aqueous going to HF and water. This K would be equal to the concentration of products, HF, all over hydronium and fluoride, which this would be the inverse of the K from above, where we have hydronium and fluoride all over HF. So they're inverses. They would multiply to get, so Ka happens to be 6.8 times 10 to the negative 4. So what does this K look to be? So the blue K happens to be 1 over the original K, which happens to be 1 over 6.8 times 10 to the negative 4. And so the blue K happens to be 1.5 times 10 to the third, which is bigger than 1, which would mean it's product favored. Kind of makes sense. So if Ka here happens to be reactant favored, it means there's more HF and water than hydronium and fluoride, because it's less than 1, it's small. If we invert the reaction, it would make sense that the number would be bigger because it would be still favored HF and water. It's just on the other side now. And that works out very well. Okay. The second way we can manipulate K is that if we multiply the coefficients by a factor, you raise K to that factor. Well, what do I mean? So let's go back to HF plus water going to H3O plus and F minus. And we're going to put coefficients. I'm going to put a 3 in front of them. Why would you do that? Well, we'll talk about that in 1 second. Which means my K expression here, I don't want to use the pink yet. My K expression here is equal to the concentration of hydronium times concentration of fluoride all over the concentration of HF. Well, what we do here is we cube everything. So we're going to cube K. So K cubed is equal to 6.8 times 10 to the negative 4 cubed, which happens to be 3.1 times 10 to the negative 10th. And so that's how it happens if we raise K to a factor. And the reason we want to do that is because the third way to manipulate K is when we add multiple reactions, we multiply Ks. Well, why would I do that? Well, let's look at one. HF, water, going to hydronium and fluoride. It has a K of 6.8 times 10 to the negative fourth. Throwing in another reaction, hydronium plus hydroxide, going to 2H2O liquid. That K happens to be 1.0 times 10 to the 14th. Well, that would be a very large K. 10 to the 12th pennies would be amazing. You'd be the richest person alive. So that's a really big K. If we add these two reactions up, well, what happens? If you notice, hydronium is gone. One of the waters is gone. And so we get a new reaction, HF plus hydroxide going to water and fluoride. So K would equal our 6.8 times 10 to the negative 4 times our 1 times 10 to the 14th. So in purple here, our K happens to be 6.8 times 10 to the 10th, which is a pretty big number. So we just made an unfavorable reaction, hydrofluoric acid and water not dissociating much, to making almost all fluoride now. So that's pretty good. So those are the three ways to manipulate K. There's one more thing we're going to talk about with K. One more thing. And that is that K, the equilibrium constant, can be expressed in terms of molar concentration which of course is molarity, or pressure. Ooh, pressure. And that will be in atmospheres. Those are only two units. So K for pressure equals K for concentration times R T delta N. Okay, so we kind of know that P is pressure. So the equilibrium constant for the pressures equals the equilibrium constant for concentration. R, of course, is the gas constant. And because we have concentration 0.08206 liters, atmospheres, moles, Kelvin, right? Because we have moles per liters, we have atmospheres, and we have temperature. And temperature, of course, is going to be in Kelvin. Then we have delta N. And delta N is the change in moles, basically. So delta N is the sum of the coefficients of products minus the sum of the coefficients of reactants. So that's what happens. And that's all we have with K at this point. So next, we'll talk about how to solve some problems in the next one. Take care.